Basically, this is chapter 4, some VLSI processing. We'll see some terminology and reflections on why there are design rules, some electrical, some physical. These slides are initially prepared by Doug Buchanan, not really my area of expertise, so I'll be basically just mouthing whatever's on the slides. Anyway, why are we looking at this chapter? Well, there's some interesting processes for sure, interesting pictures for sure, and important if anyone does go into nanotech or micromachining, and as a consequence, like to be a little bit familiar with some of the underlying processes. So here's a simple example of something that might be considered a silicone nose over here. That's to be contrasted with a silicon nose, which might be over here. And the idea behind this was you had some type of a thin film, which in the presence of a toxin would have changed colors, and you'd have picked up the color change and processed that on a camera. So the processing in terms of micromachining may not be directly evident, but it's certainly can be done in that fashion. So we'll look at VLSI processing, basically glossing over most of the details. And if you are to build a silicon chip, things that you'll need or have to do, well, you'll need a semiconductor substrate. You need to deposit or grow different materials, semiconductors, insulators, metals. You need to be able to selectively dope the semiconductor, N-type and P-type. You need to be able to pattern different layers, and that's primarily the evolution of photolithography. And you need to do all this in the correct order and with the correct materials. A little YouTube video of Santa Silicon you might want to watch. It just takes a couple minutes. It sort of shows some of the processes of creating a wafer, dicing it up, putting it onto a chip, and then it ending up in your computer. So the fabrication process for IC is primarily the selective patterning of semiconductor, dielectric, or metal on a wafer surface. So the wafer itself is the big round slice of an ingot, which is part of the processing of the individual devices. The materials can become either active or passive components. It could be transistors, it could be resistors, it could be interconnect. We're going to look at the basic material processing, some lithography, and the procedure for creating an integrated circuit. It's a very generic description and certainly not comprehensive, but it's an illustrative introduction to a CMOS fab process, and a couple of references, although I'm sure you'll be able to find a lot more on the web if you like. So with respect to wafer fabrication, well, silicon wafers are certainly the starting materials, the substrates, and the wafers basically are sliced from an ingot, and the ingot is basically a single crystal of silicon that's pulled from a molten crucible of silicon, and it's called the Tchaikovsky method, and very, very, very pure. So over on the right hand side you'd see sort of a picture of what a reaction chamber might look like, something that's able to heat up some molten silicon, and then some means of being able to pull out this ingot starting from a seed. And here's a few figures that sort of show how it starts, how it begins being pulled, and then how it pulls out as an ingot a little bit later. So it's called that Tchaikovsky method. It has very few defects and very little stress in it. It's called an ingot. It's basically a defect-free single crystal of silicon, can be several feet long, and certainly not uncommon for it to be 8 inches in diameter. So this would be an 8-inch diameter for this particular ingot, and it'd be sliced into a whole bunch of different wafers. Current state of the art at Intel, IBM, TSMC, big foundries would be 12-inch wafer lines, and so the conjecture is that moving in a few years to an 18-inch line. So in any event, for let's say the 8-inch wafer or the 200 millimeter wafer, it's roughly 600 to 700 microns thick, but all the circuitry, let's say on the top layer, the top level of it would be maybe including 10 metal layers, might be on the order of 10 microns thick, and that's sort of extracted from an image like this one where we see that this is a photomicrograph. This is 2 microns, and so going up 6 levels is about 10 microns. More recently, there's a drive to create these devices on silicon on insulator. So the silicon wafers consist of silicon films on insulating substrates, so that's where you'd form your active circuits. And these are formed on oxides such as silicon dioxide, and that would be sitting on top of the bulk substrate. 2 major types, the CMOS and the, I don't know how you pronounce the other, the BESOI, so it's a back-etched silicon on insulator. 2 processes that are made to create silicon on insulator wafers. And here's just a couple of micrographs of what that might look like in a cross section. And this first figure here sort of shows it without an active device, and the one below it with an active device. So this would represent the silicon layer in here, crystalline silicon, and this is where the devices are formed. And then separating it from the bulk would be the silicon dioxide or some insulator layer that's sort of shown in blue here. And then there's the bulk silicon below that. And as I said, sort of created by two different techniques. Here's sort of a little, I don't know if you call it a schematic or it's supposed to be a photomicrograph, but it's been colorized. So here you'd see you have your N-type devices totally separate from, let's say, P-type devices, or that could be vice versa, oxide layer and then the bulk silicon and then the wiring layers up there. So this CyMOX process, it's basically an oxide layer that's formed by ion implantation. So what that means is that you have a plasma that contains oxygen in it, and you drive the oxygen into the wafer itself, and they'll penetrate into the surface. And then you would, probably anneal out some defects, and I'm sure there's other types of processes that come into play. But you end up with an oxide layer which is buried below the surface, upon which you can put your circuits. The back-etched silicon uninsulator, also an interesting process. You basically build an oxide layer, slap another wafer on it, and then thin it down to a thickness of several microns, and then that would be where the active device would be created. Here's a little picture from an IBM slide 2009. It sort of illustrates the silicon on insulator and a silicon on bulk process. These are both planar technologies that are shown here, and still in the let's say in the silicon on insulator, you still have a separation of your N and your P-type FETs with a trench isolation. And you have the same thing with the bulk devices. But there's still some possibility down here for you forming your parasitic bipolar transistors that might contribute to patch up. But in any event, going through some of the advantages, less diffusion capacitance associated with the silicon on insulator, so less capacitance to drive. So we're going to expect to have slightly faster devices. Lower VT due to a floating body. You don't have to worry about tying your body voltages to VDD or ground like you would in the bulk. Less body effect on stacked devices. That means, like in the example of an NFET, not an NFET, an AND gate, there's a bunch of stacked NFET devices in the pull down section, and you have consequence. You have some body effect on those devices because not all the bodies are tied to the same potentials at all times. You have better. This is called a soft error rate due to the reduction in junction area. You might imagine a soft error being caused from an alpha particle. Well, alpha particle might come through here, not a problem. Alpha particle might come through here, and it could become problematic. It's immune to latch up because the decoupling of the PFET and the N-type devices, and sort of they indicate that there's a potential area improvement. And at this point in time, we'll take a brief break.